Welcome back, and this is the next in the series of videos looking at kinetics. This is Kinetics II. Now at the end of this topic you will have covered all the yellow packs, so you'll have everything you need for the Paper 2 exam. Paper 2, I'd remind you, is mostly organic from both first and second years, but it also contains some kinetics. And in this topic you're going to see how kinetics and organic mechanisms are linked. So you're going to need your notes and a calculator. So we're going to start by looking at a very simple reaction, a hydrogen atom and a bromine molecule reacting together. Now there's plenty of evidence that this actually happens in one step, and we call that an elemental reaction. Now most reactions do not occur as elemental reactions. In other words, they proceed via a series of steps. So for example, if you consider the reaction of glucose with oxygen, in other words, the oxidation of glucose which goes on inside the body, this does not happen as it's written. If you think about your collision theory, the idea that 7 molecules are all going to line up, all with the correct orientation, all in the correct energy, is just not going to happen. So this reaction, rather than happening in a single step, happens in a series of steps, and we call that a mechanism. As a general rule of thumb, you can have no more than 2 species in any single elemental reaction. So on page 3, we've got this mechanism we've seen before. We would call this an SN1 mechanism. And we need to understand how we know that this reaction works like this. Well, the reason I know this reaction works like this is because I can look at the rate equation. Now, the rate equation for this reaction is rate equals the rate constant K times the concentration of the halogenate-alkane. You'll notice that there's no mention of the hydroxide ions of the nucleophile. That's because the hydroxide ions are 0 order. They do not take part in the rate determining step. This first step is the rate determining step. This is the slow step. Once this carbocation forms, then the reaction with the OH negative is very fast. So the limit on the reaction is how quickly the tertiary halogenate alkane turns into the carbocation. So it's not dependent on the concentration of the OH negatives. From that, I can work out that this is first order with respect to the organics and 0 order with respect to the hydroxide ions. So from this, we can define the rate determining step as the slowest stage in a reaction, and it's specified by the overall rate equation for the reaction. In other words, only the species that are involved in the rate equation are involved in the rate determining step. If they're 0 order reactants, they're not involved in the rate determining step. So let's have a look at what that means in practice with an exam question on page 4. So pause the video at this point and have a go yourself at doing that one. So the first thing we need to do is we need to work out the order of reaction with respect to A and B. Remember, we can't use the balanced stoichiometric to work this out. We have to use experimental data. We're going to look at A first of all. So here we want one where the concentrations of B remain constant, but the concentration of A is changing. So we can see here we're going to look at experiments number 1 and 3, because as we go between 1 and 3, the concentration of B stays constant, but the concentration of A is times by 2. And we can have a look at what effect that has on the rate of the reaction. And here we've doubled the concentration of A, and the rate has more or less doubled. It's also been times by 2. Therefore, we can conclude it is first order with respect to A. Now we're going to look at B. And we're going to keep these 2 constant this time, because between 1 and 2, A is constant, and between 1 and 2, B is times by 2. And we need to have a look at what effect that has on the rate. And you should be able to see here that we go from 0.002 to roughly 0.008. In other words, it's times by 4, which is the same as saying it's times by 2 squared. Because here we are changing, or the rate is changing by a factor of 4, and here the concentration is changing by a factor of 2, we can say that it is second order with respect to B. and it's important in these ones that we state what we're doing. So we're looking at experiments 1 and 3, where concentration of B is constant, and we're working our way through that. So when it says justify your answer, it's very important that it is justified. So the rate equation for this reaction is rate equals the rate constant K times the concentration of A raised to the power 1 because it's first order, and the concentration of B raised to the power 2 because it is second order. Now we're going to work out K using data from experiment number 1. So I have 0.002 divided by 0.1 times 0.1 squared, and that works out as 2. Now we need to work out our units, so we have concentration per minute on the top divided by concentration times by concentration squared. So that will go down to mole to the minus 2, dm to the 6, minutes to the minus 1. Now this is usually the bit students mess up because you have to look at the units of the initial rate of the reaction, and that was done in moles per decimeter cubed per minute, not per second. So do watch that one. It's a classic mistake. Now, we need to understand what this rate equation actually means. Because I've got A and B squared in my rate equation, that means there must be a step in the reaction which involves 1A and 2 B's in an elemental step. And the reaction, or the part of the mechanism where I've got 1A and 2 B's involved, that must be my rate determining step. So let's think about possible mechanisms for this reaction, and there are lots of different ones. So we could have an A and B reacting to form an A-B intermediate. That A-B intermediate could react with another B to form a separate intermediate, and lastly that A-B plus the last B could react to form AB3. Notice in each of these steps, because we're doing a mechanism, there are only 2 species involved. And of these 3 steps, this middle one would be the rate determining step, because in this reaction I have 1A and I have 2 B's. Another possible reaction would be B plus B going to B2, and then B2 plus A going to AB2, and lastly AB2 plus the last B going to AB3. So either of those 2 are possible, and again that middle step would be the rate determining step. This last series that I've drawn out is not a possible mechanism. The reason it's not a possible mechanism is because there is no step in here which involves 1A and 2 B's. I have an A and a B cubed, but I don't have an A and a B squared. So this is not a possible mechanism. These are the 2 most common answers, and either of those are perfectly acceptable. So we're now on page 5, and we're looking at the reaction between iodine and propanone, which you did in the last pack. You did this as an experiment. You used a colorimetry idea to work out the rate of reaction, because we know that iodine is brown, but the iodide is colourless. And what you should have found is that this was first order with respect to propanone, first order with respect to hydrogen ions, and 0 order with respect to iodine. So that tells me that iodine does not take part in the rate determining step. The rate determining step is between the hydrogen ions and the propanone, CH3COCH3. You'll notice that the hydrogen ions don't actually appear in the balanced stoichiometric equation. That's because the hydrogen ions, the acid, is a catalyst. But as you'd expect, given the fact that it's catalyst, it does appear in the rate equation, because the idea of a catalyst is it speeds up the rate of a reaction by providing an alternative mechanism. So this is the mechanism that involves the hydrogen ions as well as the propanone and lastly the iodine. So I'm going to do the simplified mechanism for this one because that is the mechanism that you need to know. So we have our propanone with a double bond oxygen and CH3. And this reacts with our hydrogen ions, our catalyst, to form our intermediate. Double bond now to a CH2 group, and I've now got the hydrogen joined onto the oxygen. This is a very unstable species. It reacts very quickly with the iodine. So we're adding iodine here, and we make our product CH3. See, I reformed the double bond oxygen, and I've got my CH2I, and I've now got my HI as well. Okay, so this is my rate determining step, because this involves both the hydrogen ions and the propanone. There must come a later step, so we know this has to happen via 2 steps, because there must be a step that involves the iodine somewhere, but we know it must come after the rate determining step. So we've looked at this SN1 mechanism before. We need to remember that it's got one species in this first step. We would now change that to saying it has one species in the rate determining step, because this is the slow step. In other words, the activation energy for this step is very, very high. You're breaking a bond and you're doing heterolytic bond fission. That's going to be very slow. Very few particles will have an energy capable of doing that. However, this next step, where the nucleophile is bonding to the carbocation, you are simply making a bond, and this is going to be a very fast step. Before we go on, it's a good idea just to remind ourselves of what we mean by a curly arrow. We use these a lot in mechanisms, but you need to know exactly what they are. So they're representing the movement of a pair of electrons. Now, this pair of electrons only ever comes from one of 2 places. It will either come from a bond or a lone pair. If it comes from a bond and there's a choice, it will normally come from the pi bond rather than the sigma bond. Where it ends up is it will either end up on an atom, in which case it will form an anion, a 1 negatively charged ion, or it'll go towards an atom or between the 2 atoms, and it will form a bond. So you do need to be careful of those 2, both where you pick them up from, the lone pair or a bond, and where you put them, which is a atom to form an anion or to form a bond. So let's have a look at the tertiary halogenate alkane 2-bromo-2-methylpropane and the SN1 reaction that it undergoes. So here I've drawn out my molecule. I've already got my dipole on it, delta positive carbon, delta negative bromine. So I'm going to take the electrons from the bond between the carbon and the bromine, and they are going to go completely on to that Br. That is going to break this bond because both of the electrons have gone, and I'm going to get my carbocation intermediate. So it doesn't get put inside a box because it's an intermediate carbocation, and that Br negative has come loose and is floating around over there somewhere. Do notice it still charge balances. I'm now going to bring in my OH negative. So again, I'm going to show the lone pair. I'm not going to take the arrow from the charge because it doesn't come from the charge, it comes from the lone pair on the oxygen. So I'm going to take that lone pair and I'm going to bond it in to my carbocation, and I'm going to get my product CH3, CH3 and CH3, and my Br negative is kind of floating around over there somewhere. So this is an SN1 mechanism. Why? Because it has one species in this slow rate determining step, and then in this fast step, it has the species which is 0 order. So the rate of this reaction is rate equals the rate constant K times the concentration of the halogenoalkane. Raised to the power 1 because there's one of these in the rate determining step. So that finishes this video just looking at the start of Kinetics II. In the next video, we're going to go on and look at reaction profile diagrams and what those can tell us about the mechanism. So until then, take care, stay safe, bye-bye.